Hi girls, bear with me here. I'm using a new recording software tool and it doesn't allow me to record the whole screen. But hopefully you can hear me. That's the important part. So for your warm-up, I want you to construct a perpendicular segment from one base of this parallelogram to the other. And what did you find? So remember, what we want to do is we're thinking of constructing a line from basically the top to the bottom that's perpendicular. So we can think of that as constructing a perpendicular from one point to a point not on the line. So set your compass at a distance that's larger than the 2 from one base to the other, and then swoop on each side of the point, and then go ahead and use those as your endpoints, swooping above and below. And then you've perpendicularly bisected this segment that you created, and when you then create a segment from that perpendicular bisecting spot, that midpoint, to the point you started with, you have created a perpendicular segment from one base of this parallelogram to the other. So what did you find? You found the height of this parallelogram, okay? Or in other words, the altitude. So this is going to be important when we look into our different area formulas and shapes today. So what exactly is area? Let's define it. Area is the measure of the region bound by a figure. And area, remember, is measured in square units. So when we think about area, we're thinking about, it could be something this small. This might be like a square centimeter. It's 1 centimeter long and 1 centimeter wide. Or it might be something more like this would be a square inch. Okay, so when we talk about area, the units are important, and the measurement unit that you're using is also important. So a figure can have the same area, or a figure always has the same area, but depending on what unit you're using, centimeters, inches, yard, feet, that area is going to be slightly different. So we're going to start with the most basic formula, and that is rectangle. So many of the formulas we're going to use have their underlying theory on this area addition postulate, and that is if a figure is partitioned into non-overlapping subregions, then the sum of those areas is the area of the entire figure. Again, I apologize that part of that is cut off. You can follow along in your notes. So if we look at a rectangle, and these rectangles are specifically put on graph paper so that you can see, okay, we're finding how many square units are inside. What's important is that a rectangle, the sides of a rectangle are perpendicular to each other. Normally we call them length and width, but for our purposes we're calling them height and base because height and base are always perpendicular to each other, and we're going to be using that in the other figures that we're going to find. So if we look, right, we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 square units. Or, obviously, multiplying 3 units, squares, going left to right, times 5 going top to bottom gives you the product of 15. So the area formula, again, that we normally use is length times width, but for today, we're going to use base times height, where the base and the height are perpendicular to each other. So an example, a rectangle has a height of 4 feet and a base of 12 feet. Find its area. And then I asked you to convert your answer to square yards just so you can kind of see what that looks like. So we always want to start with our area formula. Our base is 4 feet. I'm sorry, our height is 4, our base is 12. Doesn't really matter, it's commutative, right? And then we get 48 square feet. Now, I asked you to convert your answer to square yards. You can do this a number of ways. You can start with the initial units, converting them from feet to yards, or you can think of this. A square yard is something that's 1 yard by 1 yard. So a yard, remember, is 3 feet long. So a square yard is equivalent to 9 square feet. Okay, so for every square yard, we have 9 square feet, and you can see it from the picture. So if we were to convert these square feet to square yards, we would actually take our answer and divide it by 9. And so I'm actually going to write my answer as a fraction. So 48 divided by 9 would be 5 and 3/9 square yards, which simplifies to 5 1/3 square yards. Okay. So now let's move on to a parallelogram or a rhombus. And again, this is where this area addition postulate comes into play. So what I want you to do is I want you to think about this parallelogram that we have above. Okay, I'm just sketching it out here. Think about this height here, and the base is here. If you notice, if we take this piece of the parallelogram and we move it to the other side, it fits perfectly over here. And now, remember, this is the height, and this is now the height, and this is the base, and this is also congruent. It is the base. We have created a rectangle. Excuse me. So we've gone from a parallelogram, we've rearranged it, and now it is a rectangle, and we can use our same formula that we found for rectangle. The area is the base times the height. And again, that area addition postulate coming into play. So here's another example where I just put in a couple different things. A parallelogram has an area of 18 meters squared and a base that is half the height. Find the length of the base and the height. So the base is half as, I'm sorry, I guess it should be half as tall. A little typo there. So if this is the base, right? If the base is B, then the height is going to be half B. Or we could write, the height as H and then the base as, I apologize, ladies, this is incorrect. We want to go back. We're going to let the B be base, and here's where I wanted to go with that. That if the base is half as tall as the height, then the height would be twice the base. This makes the problem a little easier to solve. You can do it both ways. You just have to make sure you're solving for the correct variable. So if the area is the base times height, but we know the area is 18 square meters, we're going to multiply B times 2B, which means that 18 is 2B squared. Dividing by 2 gives us 9 is B squared, and taking the square root of both sides gives us B is 3. And in this case, it would be meters. And so then the height would be twice that, or 6 meters. And if we notice, when we multiply 3 times 6, we get 18. For a triangle, we're going to do the same idea. We're going to use the area addition postulate, except it looks a little bit different for triangle. Start with your triangle. And again, any side of the triangle can be the base, and any side can be the height, as long as the base and the height are perpendicular. And again, it shows you that. So if you were to use this as the height, or I'm sorry, at the base, you would just have to construct the altitude from the opposite vertex. So instead of taking a piece of the triangle away, what we're actually going to do is we're going to double the triangle. Make a copy of it, and then rotate the copy, and then place it on this side D. So we're doubling it and then rotating it. So this now is the height. If this is the base, this is also the base. And what shape have we created? Parallelogram, right? So if we look at this entire shape, this is a parallelogram, but we're only interested in this area here. So if we take the entire area of the parallelogram, which is base times height, and then divide that in 2, we get the area of a triangle. So here's an example that brings back our isosceles right triangle conjectures. An isosceles right triangle has a hypotenuse of 8 inches. What is its area? So the area, again, is 1/2 base times height. I'm going to do a quick sketch here. In a right triangle, the base and the height are the legs because they are automatically perpendicular. We have an isosceles right triangle. The hypotenuse is 8, and so that means the hypotenuse, right, is the square root of 2 times the leg. So if I solve for the leg, that means the leg is 8 over the square root of 2, and each of the legs is that size. I'm not going to take time to rationalize this denominator because watch what's going to happen. So to find the area, I'm going to multiply 1/2 times 8 over the square root of 2. And I'm actually just going to square that, girls, because they're both the same. It's an isosceles right triangle. And so then 8 squared is 64. Square root of 2 squared is 2. Okay, you can simplify this a number of ways. I'm just going to think of this as 64 over 4. And so the area is 16 inches squared, or square inches. We are going to use the same technique for working with a trapezoid. Okay, a trapezoid, if we look at the trapezoid, here it is. If we double the trapezoid, make a copy, and then rotate it, it looks like this. Okay, so now we have, again, a parallelogram. This whole thing is a parallelogram, where the height of the parallelogram is also the height of the original trapezoid. But what is the length of the base of the parallelogram? It's base 2 plus base 1. It's the sum of the two bases, right? This one is the base 1, this one is the base 2. Okay? So to find the area of a parallelogram, first of all, we take half, because again, we made the copy. We multiply the height times the sum of the bases. We are going to talk about another way to look at this formula when we get into our next class. I don't want to take time on the video to do it. So this is the area formula for trapezoid, and again, you should do more than memorize it, girls. You should understand where it comes from. So finding the area of this trapezoid, this is a pretty straightforward problem. The area is 1/2 height, plus the sum of the bases. So the height is 6 because it's showing you a perpendicular distance. The bases are 6 and 14 centimeters. Half of 6 is 3. 14 plus 6 is 20. 3 times 20 is 60, and it's square centimeters. All right, girls, now it's your turn. I want you to come up with the area formula for kite, okay? And I want you to use the space below. I want you to use words or pictures, or think about what we've done in with those other shapes. And then we're also going to debrief about what other figures does this formula apply to and why. We will talk about that in our next class. After that, okay, so I'm going to skip that and I'm going to move down. So area has many real-life applications. Anytime something is covered, we're using area. So anytime you're painting, anytime you're carpeting, anytime you're wrapping something up in paper. Okay? All of those are some sort of area application. Okay? So we're going to get into more of the real-life applications here. I only have 30 more seconds on my video, so I'm actually going to stop right now. I'm going to pause the video and show you the solution to this problem in my last 15 seconds. So I only have like 15 seconds. Take a look, pause the video. If you have any questions on how I got the answer, we can debrief about it in class. Ladies, thanks for watching. Try the rest of the lesson. Do